Yeah, in this third part, I will go through a worked example. Especially, I will show you how you can set up the four different models, how to run the analysis for one of these four models, and how to display the results. And the example that I'm using is part of the package. These are data, fictitious data for network meta-analysis of relapses in multiple sclerosis. And as you can see here, there are the two data sets. One is for the IPD data, and the other one is for the standard data, the study data. And what they share is the names of the variables. That's important for the functions in crossnma. So we have here the ID for the studies, the relapses, and also for the aggregated data, the number of observations. This information is contained in this IPD data set, because here each row corresponds to a single patient in the study. In total, we have here 4 studies, and I think 1,944 rows, so 1,944 patients in these 4 studies. And so this information on group sample sizes you just get from the IPD. Treatment variable design must be either RCT for randomized controlled trials or NRS for non-randomized studies. Then we have here additional information on the ages. These are here the actual ages for the patients in the IPD. And here we have the mean age in the respective groups. Sex indicator, 1 means male, 0 means female. So you can see here in this first group, this again is an average. 20% here in this group were male, here 30%, and so on. Risk of bias information, whether the treatment that we see here is favorable or unfavorable. So 1 means it's unfavorable, and information on some bias indicator and the year. And then when we have such, this is here for binary data. If you have continuous data, what you would need there is then instead of the relapses, you would need the continuous outcome for each patient, or the mean value instead of the relapses here. And as well, information on the standard error in the standard deviation, for the study data, which you again can calculate directly from the IPD data. So then the first function you would use from the crossnma package is the crossnma model function. Here are the essential variables you have to provide for a binary outcome: treatment variable, study information, outcome of interest, sample sizes for the aggregated data, and the design indicator, whether it's a randomized study or a non-randomized study. Then you can provide the participant data, so the IPD part, and the study data. And if you only have aggregated data, you would leave this part here out and just work with this data set and so on. Then we have here the summary measure, which in this case here is the odds ratio, which is also the default for binary outcomes. But as I already mentioned in the chat, you could also use risk ratios, mean differences, or standardized mean differences. For the later two, you would have to provide here an additional variable. For that, you could have a look at the help page. Then the treatment effect variable by default is already random. So this basically says we are interested in the results of a random effects network meta-analysis. And the method we are using here is the naive approach. So here I again mentioned the 4 possibilities you have. Here we just go with naively pooling the randomized and the non-randomized study information. And the last argument here, there is a default for this, but you could also assign a prior for example, for the between study variance tau. So this is for the standard, deviation. Okay, network meta-regression. The same information as before, but here in this model, what we add is information on the covariate. And as has been already said, we have at the moment only 3 covariates implemented, and those are three arguments: cov 1, 2, 3. If there would be a need, we could extend this, but for the time being, we said let's start with this. And here with this split regression coefficients, we ask whether we in the IPD data we would like to estimate separate coefficients for our covariate within and between studies. And here we say we do not want to do this, which is a good idea if you have only a few studies in your data set. The third model, so the third possibility, using the priors, non-randomized study information as priors, is implemented by using here this value here instead of naive. All other arguments here below are optional. There are some defaults for this, but we mentioned them here in order to show you that you could control how the non-randomized studies will be fit using this method here. Okay, and then the fourth model is the bias adjusted model number 1. Here we have to provide some information, for example, whether we assume that the bias is additive or multiplicative or both. That can be mentioned here. Whether we would like to assume that the bias effect follows a common or random effects model, which treatments are unfavorable, and so on. And we can also have a covariate here additional in the model to model the bias. And the other method is basically, so the next one, just switching here from adjust 1 to adjust 2. Okay, so now I've set up all these different models, and the next step would then be to run the analysis. But before that, let's have a look at the net graph. This is here the net graph for model 1, but I could also use here model 2, 3, and so on, because the network graph you get is just the same, because the data that we put into the analysis is the same data. And here we see that this is here fully connected. What you do not see is that the aggregated data are only here from this A versus D comparison. So all other information comes from the IPD part of our analysis. And one thing why you should have a look at the network plot is that it could be that your network is disconnected. The model procedure or the model fit works even for disconnected networks, but you get there some nonsensical answers. So you should only use this method if you have a connected network. So, and then the next function that you can use then is the crossnma function. You input the model file. This is basically the only information that you have to provide, but typically you would like to control how many iterations you are using in the JAGS run, how many iterations you would like to use for the burn, and so on. And then if you run this, which takes a little bit of time depending on how fast your computer is, then you in this JAGS fit result you have the results of your network meta-analysis. This year model 3 was the one where we use the non-randomized studies as priors. And then if you just type in the name here, JAGS fit 3, then you get a printout that looks quite like this here. This is here formatted and so on. But basically, this is here the information. We do not get here an estimate for treatment D because we said this is our reference treatment. If I go back, I think I did not mention this before. Yes, so here what I used here is I said the reference for in our model should be D, or treatment D. By default, the first alphanumeric treatment is being used. So in all other models where we do not use this argument, it would be treatment A as the reference. But here we specifically said, okay, we would like to have D as our reference treatment. And if we do that, we do not get a result for treatment D, but we get then the relative treatment effects of all other treatments in comparison to D. And the mean here is basically the odds ratio comparing treatment D with treatment A. So we see that there are many more relapses with D compared to A. Standard deviation for the log odds ratio, as well as here the limit, basically the credibility limits, the median value for the comparison D versus A, and also here for the other bits, tau, the standard deviation for the log odds on the log odds ratio scale, and this here is then because we did a network meta-regression. This is here the age effect that we get in our model with the corresponding variance estimator for this covariate. And then we can also produce league tables, either a league table in a wide format, or here said here in a long format. As we have a network meta-regression, we have to specify here a value for the covariate that we would like to calculate these values for, which is probably another nice presentation is using a heat plot, so a league table as a heat plot, and again for the same covariate value here, and here we can then directly see all comparisons for various combinations here of two treatments. And then there is also the possibility to check how good the JAGS fit is. And for that, you can use the plot function. And then you get here, these plots, which should look quite random. And I would say this is more or less okay here in this case. And that's basically it for the analysis. So little bit on the limitations and of the package and our future plans. So what's completely missing at the moment in crossnma are methods to evaluate inconsistency, either local or globally. Also, we do not have any ranking methods implemented, such as Sucra scores. And what's also missing is support for counter time to event outcomes. So this was one question in the chat. So time to event outcomes, hazard ratios at the moment are not implemented and could not be used. Concerning the first two bits here, one idea would be to link or to use methods which are available in NetMeta, which provide these methods, and also to use them for an output from crossnma, but we did not really work on this already. Okay, so at the moment, version 1.1.0 is available on CRAN, so you could just install it here with this command. The latest version, which at the moment is basically this one here, is available on GitHub. And there are help files for everything that I've shown you, for all commands, and also a vignette. The vignette uses the same example as I used here during the presentation. And we are working on a manuscript to illustrate the functions. And if you have any comments, questions, you could send us an email. And the other possibility would be that we have a brief chat or discussion about this. Yeah, that's it from my side, and I'm happy to answer any questions.